Howdy, this is Browdy coming at you with discussion 8.3, all about limiting reactants, or as you'll see here, limiting reagents. So I'll explain what the difference, if any, is there. So I say let's go ahead and get started. So like I said, discussion 8.3 is all about limiting reactants, and you'll notice that I've got limiting reagents written, and those two, as far as we're concerned, are the same thing. Reactants, reagents, you're going to see it both ways, and so I figured we might as well have both just right off the bat. So we see those if you're in other chemistry classes down the road, or if you see it in college, or maybe another science class uses the term reagent. I'd rather you just see both and be familiar with them. I personally plan to use the phrase or the term reactant, but both work, both will be used, so just be familiar with each. Now, what a limiting reactant is, you'll remember hopefully from Discovery 8.3, if you did the Discovery and you're watching this, that we basically made s'mores, and the idea of making s'mores was that we had marshmallows, graham crackers, and chocolate, and we were going to run out of one of those first as we were making s'mores, and whichever one we ran out of first was going to be the one that limited how many s'mores we could make. We call that the limiting reactant. And so what a limiting reactant actually is, in terms of chemistry as we will define it, is the reactant that determines the amount of product that can be formed by a reaction. So it's the reactant, the thing, the ingredient, essentially, that determines the amount of product that could be produced ultimately by the reaction. Now, the opposite of the limiting reactant is the excess reactant. You might have heard the term excessive before. That means the same thing as in excess. And so the excess reactant is the reactant that isn't completely used up in a reaction. You might remember back in 8.2, you probably saw some questions that say, so-and-so amount of this reactant reacts completely with this, or reacts with excess blank. The reason we saw that before is saying, hey, there was enough of this that reacted with excess this, so we didn't have to worry about limiting or excess. There's plenty, is essentially what that was saying in 8.2, so we didn't have to worry about this. But here in 8.3, we're going to get a little more in depth, and what you'll find out pretty quickly is that we actually already know how to do just about everything we're going to do in this. I think this will be a pretty quick discussion. So example 1 here, I'm going to read the question and then I'll explain everything. It says, when 36 grams of H2O are mixed with 67 grams of Fe, iron, what mass of iron oxide is produced? What is the limiting reactant or reagent? It gives us an equation to balance and then a problem to solve. So there's a few components to this. It gives us 36 grams of water and 67 grams of iron. Those are the amounts of each reactant that we're starting with. And it wants to know what mass of iron oxide is produced. So what we have to do first is figure out how much iron oxide we could make from our 37 grams of water and how much iron oxide we could make from our 67 grams of iron. Whichever one of those makes the least iron oxide is going to be the limiting reactant. It's going to be the one that will run out first. That'll determine our limiting reactant, as well as how much we can make. So that's the concept, but really what we're doing, all of this we've done before. Let's underline first. You know I'm all about underlining, so I've color-coded things here. And so first I underlined 36 grams of H2O. I underlined that in blue so I could show you that I did that here. I underlined 67 grams of iron in green so you could see when I worked with that here. Those two are my two reactants, so I underlined those. Mass of iron oxide is what I'm looking for, so I underlined that in purple so you could see when I was working with mass of iron oxide. And then the limiting reactant, I like to underline that at the end just so I don't forget to answer that question. And I underlined that in orange. It looks kind of yellow on here. And again, just so you could see what corresponded with what part of the question. I'm not expecting you to do this at all, but I think it's helpful to at least look as we're learning. So I'm going to go through and I'm going to set up my 36 grams of water and figure out how much iron oxide I can make from that. I do it exactly like we did in 8.2. I started with 36 grams of H2O. I put it over 1. Now you'll notice I'm not canceling units here. That's just because there's so much going on. I think canceling units would make it look a little bit more busy. I trust at this point that you know to cancel units if it helps you. Started with 36 grams of water, and we're in grams of water. So I need to, well, actually, I'm getting ahead of myself. I need to balance my equation first. We look at our equation. Sorry about that. Man, Mr. Browdy, I almost got ahead. So I've got iron plus water gives iron oxide and H2, hydrogen gas. So to balance, we see that there's 3 iron over here and 1 here, so I put a 3 in front of it. Now I've got 4 oxygens here and only 1 here, so I have to put a 4 in front of H2O. That means I now have 8 hydrogens, so I have to put a 4 in front of H2, and we're balanced. Now we can go to where I was going before. So I've got my 36 grams of water. That's my first reactant, and I want to see how much iron oxide I can make with 36 grams of water, assuming that I had an infinite supply or excess of the other reactants. So I take 36 grams of water, and I'm in grams of water, and I want to get to grams of iron oxide. So I do that through moles. So I have to go from grams of water to moles of water. In 1 mole of water, there's 18.02 grams. That's the molar mass. I found that on the periodic table. Oxygen plus hydrogen plus hydrogen. Now I'm in moles of water, and I want to go to moles of iron oxide. And I do that with the mole ratio. I look at my equation, and I want to go to moles of iron oxide, so that's on top. And there's 1 mole of iron oxide for every 4 moles of water. And so I set that up just like this. And now I'm in moles of iron oxide. And lastly, I want to get to grams of iron oxide. And so I go from moles to mass using molar mass from the periodic table. I add up iron plus iron plus iron plus oxygen plus oxygen plus oxygen plus oxygen, or 3 times iron plus 4 times oxygen, however you want to do it. And I get 231.55 grams of iron oxide in 1 mole. It's the molar mass. I then do 36 times 1 over 18.02 times 1 over 4 times 231.55, and I end up with 115.65 grams of iron oxide. And you'll notice I didn't circle it. And I would encourage you not to circle anything until you've completely solved both problems, and I'll show you why here shortly. So for now, we know that I can make 115.65 grams of iron oxide from 36 grams of H2O. And I put this in purple so we know I'm talking about mass of iron oxide. That might help you, it might not. No big deal if not. But now I've got 67 grams of iron. So I want to know how many grams of iron oxide I can get from my 67 grams of iron. So I do the whole thing over. I go from 67 grams of iron to moles of iron by dividing by molar mass. I find that on the periodic table to be 55.85. I then multiply by the mole ratio, and there's 1 mole of iron oxide for every 3 moles of iron. So I've got that here. Now I need to get to grams of iron oxide, and I use molar mass of iron oxide, which I already used before, so I just use that same number. It's the molar mass, and I'm done. I multiply it out, and I get 92.59 grams of iron oxide. Now, obviously you're seeing the completed product. I wouldn't have circled anything yet. And I look, and I see that 36 grams of water can give me 115 and some grams of iron oxide, whereas 67 grams of iron only gets me 92.59 grams of iron oxide. So I go ahead and I circle the smaller number because I can only make the amount that the limiting reactant will allow me to make. I will run out of iron oxide before I run out of water because this makes less iron oxide. You know what I mean? It's like if I have enough s'mores, or if I have enough marshmallows to make 250 s'mores, but I only have enough chocolate to make 10, well then chocolate's the limiting reactant and I can only make 10 s'mores. And it's important that you also say that iron, in this case, is the limiting reactant. And that's why I underline that in orange. And that's every step. It seems involved, but there's really not much to it. I figure out what I'm trying to get. I see what I start with, and I see what I can get based on this, what I can get based on this. Whichever one makes the least is the amount I can make, and then that reactant is the limiting reactant. Let's try another example. Excuse me. Oh, skipping on me. And there we go. So example 2. It says, what is the maximum number of grams of aluminum chloride that can be produced from 32.4 grams of aluminum and 170.2 grams of chlorine? What is the limiting reagent or reactant? Gives me the equation Al plus Cl2 yields AlCl3. And because I forgot last time, let's just balance this sucker right off the bat. I've got 1 aluminum here and 1 there, so for now I'm good. But I've got 2 chlorine here and 3 here. And 2 and 3 don't go into each other, so we like crisscross, right? We try to make them 6. If I put a 3 in front of this chlorine, I have 6 chlorine. If I put a 2 in front of AlCl3, I've got 6 chlorine. But now I've got 2 aluminum, so I put a 2 in front of that, and I have 2, 3, 2, a balanced equation. Now I look at my question, and I underline the things that I need, right? So maximum number of grams of AlCl3. That's what I'm looking for, so I'm going to underline that in purple. And again, you don't have to do that. I'm just doing this my way. That can be produced from 32.4 grams of aluminum. That's the first reactant. I underline that here in blue. And 170.2 grams of chlorine. I underline that in green. And then, of course, what is the limiting reactant or reagent? I underline that in orange so I can correspond there. So I take my first reactant, aluminum, and I try to see how many grams of aluminum chloride I can get from 32.4 grams of aluminum. So I start with that over 1, and I go from grams to moles of aluminum. Because it'll always go from if I'm going from grams to grams, I'll start with grams and go to moles of that substance, then moles of the desired substance, and then grams of the desired substance. So I take the molar mass of aluminum and divide by that, right? I start with 32.4 grams of aluminum and I divide by 26.98 to get moles of aluminum. Now I use the mole ratio to convert to aluminum chloride, and there's 2 moles of aluminum chloride for every 2 moles of aluminum. Boom, mole ratio. And now I'm in moles of aluminum chloride and I want to get to grams of aluminum chloride. So I add up Al plus Cl plus Cl plus Cl to get 133.33 grams of aluminum chloride. I multiply it all out. 32.4 times 1 over 26.98, or divide, times 2 over 2, times 133.33, and I get 160.11 grams of aluminum chloride. Now, I wouldn't have circled it yet. Now, I do my second reactant. I have 170.2 grams of chlorine gas, so that's Cl2, so be careful. Now, I want to convert that to moles of chlorine, so I divide by the molar mass. And remember, Cl2 needs to be, so chlorine is 35.45, and I multiply that by 2 to get 70.9. So that's my molar mass, and I divide by that to get moles of chlorine. Now I need moles of aluminum chloride, so there's 2 moles of aluminum chloride for every 3 moles of chlorine gas, and there's my mole ratio. And then lastly, I use the same molar mass of aluminum chloride, I multiply it all out, and I get 213.38 grams of aluminum chloride. So what that means is that my 170.2 grams of chlorine gas could get me up to 213 and some grams of aluminum chloride. But my 32.4 grams of aluminum can only get me 160.11 grams of aluminum chloride. So aluminum is my limiting reactant, and the most that I can make is 160.11 grams. And that's it. Everything that we just did, we've done before. We've known how to do. We're just adding a new term and adding an extra step. Now that's it for limiting reactants. Quickly, we're going to add one more concept, and it'll be nice and quick. And this is the idea of percent yield. So we need 2 terms that we need to understand before we understand percent yield. So theoretical yield is the maximum amount of a product that could be formed from the given amount of reactants. So that's what we just calculated when we found the limiting reagent or the limiting reactant and how much could be made, like we did in number 2. Well, we found out the maximum amount that could be produced, and that was 160.11 grams of aluminum chloride. That's the theoretical yield. That is the maximum amount of that product that could be formed given the amount of reactants that we had. But there's also the actual yield, which is the amount of product that actually forms when the reaction is carried out in the laboratory or in a lab. So how much did you actually get when you did that? Was any lost along the way? Did any human error happen that made you get a little bit less? And so the way we calculate percent yield is actual yield divided by theoretical yield times 100. And I have percent in parentheses here because you're making it a percent. You're not actually multiplying by 100%. 100% is just 1. So actual over theoretical times 100 to give you a percentage. So let's look at this very last problem. Question 3 says 12.7 grams of copper, I underline, produced 38.1 grams of silver in lab. And I underlined that and I specified that that's the actual yield because it produced, or that much was produced in lab. Actual yield. What is the percent yield of silver in the reaction? I underline that because that's what I'm looking for. And then here I see a single replacement reaction. Copper plus silver nitrate gives you copper nitrate and silver. I balance it, and you can see here the balanced equation, and I get to work. I start with 12.7 grams of copper, and you'll notice I only have one reactant this time, and that's okay. So I'm only calculating for one reactant. I've got multiple reactants, but I have 12.7 grams of copper over 1. And I want to convert to moles of copper so I can convert to a new substance. So 1 mole of copper weighs 63.55 grams. Now I use the mole ratio to go from moles of copper to moles of silver. So there's 2 moles of silver for every 1 mole of copper, and boom, there's my mole ratio. And then already I'm at the last step. I just need to convert to grams of silver, so I multiply by the molar mass. There's 107.87 grams of silver in 1 mole of silver. I multiply the whole thing out, and I get 43.11 grams of silver. And I don't circle that yet because I've just calculated my theoretical yield. That is the maximum amount of product I could get from 12.7 grams of copper. But in lab, we only got 38.1. And to find percent yield, I take 38.1, the actual, divided by 43.11, the theoretical, multiply it by 100, and I got 88.38%. So what that means is, out of all the possible product I could have made, I was able to make 88.38% of that in lab. So of all the possible maximum product, I was able to yield 88.38, or I had 88.38% yield. And that's it. That is all of discussion 8.3. Very little of that is new. Percent yield, sure, but we've done percent error before. This is very similar. Limiting reactants, sure, but we've done stoichiometry. We've done conversions before, so this isn't actually anything that new. So I hope this is helpful. I hope the color coding helps. And as always, if you have any questions, Canvas message me, email me, ask me in person, and I'll be happy to help. So I hope all is well. I hope this has been helpful, informative, dare I say even entertaining. And I will see you all in the next one. For now, take care.